All right, so these are classic. These are awesome distance problems. A lot of times you'll hear something like, a train leaves the station at 2 p.m. Heading towards Chicago at 40 miles per hour. 2 hours later, a train leaves the station and at 60 miles per hour going towards Chicago. When will they crash into each other? Um, I'm not gonna do trains. I'm gonna do seagulls and ravens. Uh, I don't know, just to be rebellious or something. But the problems work the same way. Um, and this is an application of the idea of weighted averages. You'll see when we write the equations, there's that kind of concept of weighting things differently. Um, but before we start, let's just kind of establish a key part of this making sense is the idea that distance is equal to speed times time. So if you're going um, 50 miles per hour for 2 hours, you um, you go 100 miles. And just look at the units here. So 50 miles per hour. That's how we'd write that, miles. 50 miles over 1 hour, basically, times 2 hours. Um, the hours would cross out, and I should say 50 miles. Uh, so you've got 50 miles times 2 equals 100 miles. Okay, so that's how that works. Um, so when you're doing distance, speed, and time, your speed, if it's miles per hour, then your distance will be in miles and your time will be in hours. If your speed, as we're doing in these problems, is meters per second, your distance will be in meters and your time will be in seconds. So those units all work together, right? And then the basic relationship is distance equals speed times time, and you can rearrange this, solve for speed, solve for time, whatever. So, all right, so let's get into this. A seagull flies at 15 meters per second, and a raven flies at 10 meters per second. Um, if the seagull and raven fly away from each other, how long will it be before they are 1,000 meters apart? So let's just diagram this. They're starting, it's at a certain place, um, and they're flying away from each other. Okay, so let's say the seagull goes this way. It's going to go this way at 15 meters per second. Oops. Meters per second times t. Let's call it t. T seconds. So when we do 15 meters per second times t seconds, we'll end up with a certain number of meters, just like this. Um, we did 50 miles per hour for a certain number of hours. What we're left with is a certain number of miles. So this part of the equation would describe the distance this way. 15 meters per second times a certain number of seconds will be whatever distance the seagull can fly in that number of seconds. Okay? But the raven's going to fly the other way at 10 meters per second for the same number of seconds. Right? So the question is, how long will it be? I mean, they're dealing with the same reference for time. They're going to start at the same point. Boom, I'm going to start the stopwatch, and then when they're 1,000 meters apart, then they're 1,000 meters apart. They'll be 1,000 meters apart from each other at the same time, right? Okay, that might be saying something that's unnecessary, but okay. So this is the situation. It's starting at a certain point. One's flying at 10 meters per second for a certain number of seconds in this direction. The other is flying at 15 meters per second for that same amount of seconds this way, and at a certain point, they'll be 1,000 meters apart. So that's our basic setup. So this is essentially our equation. We just need to write it out in a little bit of a cleaned up form. So we just do 15 meters per second times t seconds will be the distance that the seagull can fly in however many seconds that is, plus 10 meters per second for that same number of same amount of time is going to equal this total distance between them, 1,000 meters. Okay, so we can combine like terms. 15 plus 10 is 25, so this is 25t equals 1,000 divided by 25 divided by 25. So 1,000 divided by 25 is 40. So it would take them 40 seconds to fly 1,000 meters, or a kilometer away from each other. Okay. So let's keep going. So suppose the situation were reversed. A seagull flies at 15 meters per second, and a raven flies at 10 meters per second. Suppose they are 1,000 meters apart, and they fly straight at each other. How long will it be before they collide at top speed? Right? So it's like they fly away from each other for 40 seconds, and then they fly back, and because they're like, I changed my mind. Oh wait, no, I'm mad. I'm gonna crash, collide. Okay. A seagull. Okay, so how do we set this up? So let's diagram this. Okay, so they're gonna collide at a certain point. That's our explosion. Our bird explosion. Okay, and so the raven is gonna fly towards his doom. Need a color. At 10 meters per second for a certain number of seconds, and then the seagull. Make this longer. The seagull will fly at 15 meters per second for that same amount of time, t seconds, and then they'll crash. And they start out 1,000 meters apart from each other. Okay, look at this diagram and look at this diagram. Is this not the same basic problem? This problem is just this one in reverse, or this one is this one in reverse. So you can think of it, imagine running this one backwards. They start at a certain point and they fly away from each other until they're 1,000 meters apart. Well, play that in reverse. And it's like they're colliding, or i.e. they're meeting at where they started up. So if they start out a certain distance apart and then they're flying towards each other, it's the same exact setup as if they start out collided, if you will, and then fly a certain distance away. So we would set this up again, 15t plus 10t equals 1,000. Same setup. I want you to see that visually, just see how it is the same. All right, so different type of problem here. A raven begins to fly toward Heliopolis at 10 meters per second. A minute later, a seagull begins to chase him, flying at 10 meters per second. How long will it be before the seagull catches up? Right? So this is a slightly different kind of problem. All right, so a raven begins to fly toward Heliopolis at 10 meters per second. A minute later, okay, we want to convert that unit, right? Instead of a minute later, that's 60 seconds later, right? Don't fall for that trap, even if I set that trap for you. 60 seconds later, a seagull begins to chase him, flying at 15 meters per second. How long will it be before the seagull catches up? So let's diagram this. So a raven is flying. Now it doesn't matter. I mean, it could be just it begins to fly in a certain direction. That's all that means. So a raven is flying leaves at a certain time and flies 10 meters per second for a certain amount of time. Now, um, so let's see how to visualize this. Let's say, let's call this a 60-second head start. So now the seagull is going to fly at 15 meters per second for a certain amount of time. But essentially, the Raven has a head start of 60 seconds. So you can think of this as t minus 60. So the seagull is going to fly for 15 meters per second, but for 60 seconds less. For 60 seconds, what would you call that? The amount of time that he has in the air flying is 60 seconds less than the Raven, because the Raven got a 60-second head start. If that makes sense, okay? So what we want to know is how long before they catch up, meaning when will they have the same distance. So what we just do, so 10 meters per second times the amount of time that the Raven is flying will be his distance. And we want to know when that's equal to the distance that the seagull flies. So what's the distance that the seagull flies? It'll be 15 meters per second times the amount of time that the Raven is flying minus that 60-second head start. Okay? So now you can just solve for t. So let's distribute. Actually, you know what? Before I'm going to distribute, I'm going to factor out. I'm going to divide both sides by 5 just to make it simpler. See how there's a 5 in the 10 and a 5 in the 15. So this we could simplify. 2t equals 3t minus 60. And then distribute this 3t minus 180 equals 2t. You could subtract 3t from both sides. So I've got negative 1t, 2t minus 3t is negative 1t, or negative t equals negative 180. So t is 180 seconds, also known as 3 minutes.